Hello. So here again we have another example to illustrate to you the order of reagent set matters in electrophilic substitution of benzene derivative. So for this example, let's begin with a methyl benzene molecule. And our two sets of reagent here, set 1 will be concentrated nitric acid with concentrated sulfuric acid. So in organic chemistry, you could just represent concentrated by using this abbreviation C dot, or you can just put CONC dot. Okay, both are fine. Set 2 reagents will be bromine in a halogen carrier, iron 3 bromide. This must be anhydrous for it to function as a halogen carrier, to plot the Br minus and to generate the electrophile Br plus. So suppose we start with set 1. And we throw in con HNO3, con H2SO4. So this step puts on NO2 onto the ring here. Now let's take a look. The only substituent of the original substrate here is a methyl group, which is an R group. So this R group here is electron donating group, and it is activating. Although it's a bit weak, but still activating, and it is 2,4 directing or auto para directing. So we have your auto position and the para position that you can put on the NO2. So the resultant product here, you have a mixture of these isomer, a 2-nitro methyl benzene and a 4-nitro methyl benzene. And after this step, when we put in this bromine, where does it go? Now here we have two directing groups, the methyl group and the nitro group. Let's analyze one by one. This methyl group here, again, is activating, same as here, we don't change it. So if I have a second electrophile here, Br plus, this guy, the CH3 will want it to go to where? It will, according to itself, is 1, so 2, 4. That means you prefer to put it here. See my arrow? But for this NO2, to itself, it is what? Deactivating, but it's 3 directing. Remember? Meta directing for all these polarized pi bond substituents. So, meta. Can you see meta? 3 directing. So, it will prefer to be at the third position of itself. So, 1 is itself, 2, and 3. So the arrows are the same position. Same for the other molecule. The green arrow is for the methyl group. So 2, 4, but 4 is being blocked by the NO2, so no chance. Must be here. And for the NO2 is 1, 2, 3. So it's here. Now, this makes very good reaction because they have what we call a common target. That means the substituent groups, they both direct the next guy onto the same position. So from here, you see that the next one will go on to the position next to the methyl group. So a bromine is going to come in. After I put in the Br2, FeBr3, you generate this electrophile, Br plus. Okay, let's fill in the rest of the gap. NO2 here, fine. Now for this molecule, you could draw for us here, Br, NO2, CH3. That's if we place the Br over here. But if we place it there, we would have this molecule, which might not be formed at all. And the reason is very simple, because there's so much space over here. Why we want to incur some energy penalty? Because steric hindrance and group itself around this electron cloud here. So if you are encountered with this situation, please either put this as minor, that means it's not of a high proportion, or we do not even form it at all. So the major product from this pathway will just be these two molecules. Now, if you change the order of adding set 1 and 2, That means we begin with adding the bromine first. Br2, Fe, Br3. Likewise, in the first step, the Br could go here and the fourth position. Okay? There's no debate. Both will be formed equally likely. However, in the second case, when we add the corn nitric acid, corn sulfuric acid, methyl group here prefers it to go to where? Here, right? Ortho and para. Ortho, para's being blocked, so no chance. But for the bromine, bromine also like it to be at its own ortho and para. Do you see? It's ortho, para's blocked. So what happens is they have conflicting instructions. They do not have a common target. CH3 wants it to go to the position of the green arrow. Bromine wants it to go to the red arrow. So how? The next substituent here, which is your NO2, will be slightly confused. So it could be random, but let's analyze. Bromine is electron withdrawing, is deactivating, whereas the methyl group is activating. So you could have some mixture of products. And remember, they do not like to stick together 1, 2, 3 tri-substituents, so I'm not going to draw it for you. But you could have other possible answers. Like this case, NO2 is here, or NO2 on this side. And if you look at this, if I put the NO2 here, we would get NO2, CH3, Br is there, and we also have the last molecule, which is Br, CH3, and then the NO2 is here. So we could have these 4 isomers, which means to say that this reaction is not so desirable because you can have a mix of these isomers. And as for the proportion, it depends on the chemical reactions condition like temperature, pressure, the amount that you add. So for this syllabus, we'll just go with the one that helps the reaction. So now we are comparing bromine against methyl group. Bromine says, do not come in because this guy is deactivating. It doesn't want further substitution. But the methyl group says, oh yeah, please come in, I welcome you. This is activating. So you go for the one, you listen to the one that helps you. So activating directs it, methyl group wins. Your major product in this case would be this one, the one that underlined, as well as this one here. So that's our conclusion, and I hope you really understand what's going on here. If not, please revise this video again.